Hello, everyone. Welcome to our meetup today. It's about design
Hi.
principles versus performance. With me are Igor and Kenny. Kenny will be the presenter today. He's from Germany. We had it already once in our meetup group, more than a year ago. And yeah, the today talk will about design principle versus performance. And yeah, we are very interested what we will hear today. Before we start, a few words. As usual, first, I want to say something about our sponsor, Microsoft. Microsoft has these new Azure Immerse workshops. They are about different Azure topics, how to migrate your applications to Azure. So you can take a look. And yeah, the workshops are free, so you can register online. This is the link, so please take a look. Then another announcement I want to make is about the Global Azure event. So previously, the previous years, it was called Global Azure Bootcamp. Now it is rebranded to just Global Azure. It's a online event, as you would expect. And this year it takes place on April 16. It's a worldwide event. All the user groups, worldwide are doing this event. And it's about a lot of different topics related to Azure and cloud solutions in general. So go to globalazure.at to find out more details. And also, if you're interested to give a talk, the call for sessions is still open and you can submit your application. Yeah, that's basically from my side. If you have any questions to us or you want to also speak at our meetup, just write me or Igor. And yeah, we would be happy to have you as a speaker in our meetup group.
Definitely.
So now I give over to Igor.
Thanks, Bernd. I just want to say a word or two about our today's meetup. So it's a bit special. So it's a part of our high performance area. So I guess, Bernd, I will mute just for a second there. So it's a part of our high performance series. So most of you know, at least twice per year, we are trying to have talks which are dedicated to performance. And I'm happy to have Kenny here today with this topic, which is definitely relevant. So Kenny also gave another one, high performance talk a bit more than a year ago in Graz, and it was really awesome. So I'm looking forward to this one, and I'm also happy to announce the next one, which we'll have this year, which we will be given by Konrad Kokosa. For those who do not know him, Konrad is a well-recognized expert in .NET performance, definitely, and he's an author of this Pro.NET memory management book. The book is a must-have for everyone who cares about performance in .NET. I highly recommend the book. It's definitely must-have. And aside for the book, Konrad does a lot of other activities in the community. So he recently started, stumble up of this, he recently started actually translating the book in a series of YouTube videos. So if you're really interested in a .NET garbage collector internals, like how it works and so on, I suggest to take a look on the .NET channel where he actually explains how .NET Garbage Collector works internally. And also aside of this memory part, he also does courses which are all somehow related to performance. The newest one, which is coming out now in March, is called .NET Diagnostics Expert. So you can see what it is about. It's definitely diagnostic .NET apps with the plenty of deeper look with the plenty of cool stuff on it. The links will be there. I just wanted to say I'm really happy that this year we will have two awesome speakers in our high performance series. That will be it from my side, and I would like to now to leave the stage for Kenny. So Kenny, please take over.
Yeah. Thank you guys for joining my talk about design principles versus performance. And this is an anecdotal talk, which means that I will first start with some things, namely how I structured my apps in 2015, round about that year, or up to the year 2015. And when I'm finished with that and we have a common ground how I structured my apps, I will then show you some performance characteristics of different operations in the .NET Runtime. And after that, the main part starts where I want to cover what I learned about the .NET Runtime internals, mainly the memory management and the garbage collector, and the asynchronous programming part with the TPL and async await, how these are implemented from a high perspective. I won't go into many details. The main subject of these sections is to give a common ground so that we can then go into the last part of this talk, where we talk about, well, how are design patterns and design principles, structures, maybe especially with a focus on new programmers, and what is good about the solid principles, for example, what is bad or what could be improved upon, and is there maybe a way to introduce new principles or new patterns or a new structure of our applications so that we can argue about performance while also keeping the greater design of the software application in mind. So this is what we're going to talk about in the next minutes. Okay, about me. My name is Kenny. I'm working at Synotech. We produce individual software for our clients. I'm also a PhD student at the University of Regensburg in Germany. And you can follow me on Twitter, on GitHub, or on YouTube under the handle Feox. It's FEO2X. All right, so let's jump right into it. How did I structure my applications up to 2015? I usually wrote many small classes. And what's common about these classes is that there is a single piece of functionality in them. And I also introduced an interface or an abstract base class around these classes, so that when I want to call other functionality, I always do this through some kind of abstraction so that the callee can be replaced without the caller knowing. So the common principle of loose coupling that you know for sure was one of the main drivers of how I structured my code in the most primitive way. And the resulting object graph was, of course, resolved by a DI container. So I used a lot of dependency injection. And yeah, what I ended up with was usually a large object graph of really small objects that really did one piece each. What was also common is that I hadn't many if-else or switch blocks in my code, because I rather focused on loose coupling when branching too. So what I would usually do is write an abstraction where two members are present, and one of these members is for the corresponding objects that implemented this abstraction to indicate, hey, I'm the right object for this kind of if-else block, or for the corresponding case. And then there was a member that I invoked to actually execute what should happen within the corresponding branching logic. So also a lot of loose coupling here. Of course, I try to use established design patterns and, of course, test-driven development. And just so that you can get a quick overview of the design patterns I cared about. So there are a lot of design patterns that relate to object construction, to behavioral design patterns, and maybe Memento for redo undo functionality, or something like repository unit of work for data access, or for unit tests, and so on. I think most of you will know many of these design patterns too, so I won't go into details. And of course, there's also a way to talk about the whole software architecture. Like in this case, I have an N-layer architecture with a presentation layer and an application layer and the business layer and the data access layer. And each of them takes on different responsibilities. They all have a dependency on framework or library code or even runtime code, which is represented as this infrastructure bar on the right side. And of course, in 2015, we also had ideas about making the business layer the core of our architecture. So we have something like the ports and adapters architecture or the onion architecture, which was also quite influenced by the domain-driven design movement, where the business logic is in the center of the application and it can run independently of any other infrastructure. Yeah, and that's what was in my toolbox back then. This is how I structured my code mainly. But what about performance? The first thing, I was a teacher for students at the university from 2013 to 2015. And the first time I prepared stuff or teach them how to program in an object-oriented way, I also toppled about this topic. How are we actually teaching performance to other students, or is performance something that is prevalent when we design our apps? But before we go into the details, I want to quickly show you the performance of everyday things. So what is performance of everyday things about? I will show you some operations like invoking a method via a static method or an interface and so on, and doing other operations, and we'll put that into relation how the performance of each of these operations is, so that you get a basic understanding about how costly is a type of operation. And of course, as we will talk about time, I just want to put it back into your mind how the time scale is actually represented. So I'm sure everybody of you knows seconds and milliseconds, but I'm not sure if you get the order on the left side totally right. So if you couldn't, this is just a quick reminder. When we talk about nanoseconds, these are smaller values than microseconds, and on the left is picoseconds. This is 10 to the power of minus 12. So just that you have a basic understanding about the scale that we're working in. So we will be mostly in the green and yellow areas today. All right. Cool. Okay, so just a few short words about the .NET Runtime, which I'm sure you already know. If we compile our C# code or F# code or Visual Basic code, it doesn't get translated into machine code directly, but it becomes a Microsoft Intermediate language, which is some kind of byte format. And when we start our applications, the .NET Runtime is started too. And this .NET Runtime consists of several services. And we will take a look, of course, at the garbage collector today, which the basic job of it is to allocate and deallocate memory for us in the managed heap. And we will also have some threading tools and so on. And also a major part of the .NET Runtime is the just-in-time compiler, or the JIT in short, which takes our MSIL code and translates it to machine code during the runtime mainly. There is an option for ahead-of-time compilation, but I'm sure you already know about that. So the thing that we will be talking about, or the things that we will be talking about today, is mainly the garbage collector and the threads and the thread pool. All right. So let me quickly show you some code. I've created a few benchmarks with benchmark.net, and I just want to quickly show you what we're going to see the results for. So in these imperative and multi-threading benchmarks, the basic operation that is done in every benchmark here is to increase a count variable. This is either a static variable or a member of a class, as you can see here, and these are either always increased in a single operation. And we do this in different ways. So we call static methods, or we call an instance method on an object that we created beforehand, or we call this stuff via an interface, or via an overridden method, or via a delegate. Or we create a completely new struct, or a completely new class instance, so an object on the managed heap. Or we increment using a primitive for thread synchronization, the lock over here, which internally just calls the monitor into the monitor class. Or we throw an exception, immediately catch it, and then increment the count. Or we also run this count increment, the incrementation of the count on a background thread on the thread pool using task run. Or we even start up a new thread where we increment the count and wait for the result. And I also have a few other benchmarks, like some data structures. So the basic thing that I did here is I created a collection versus a dictionary with either 100, 1,000, or 10,000 entries each. And I always search for the last item within the collection. And I want to contrast this with the performance characteristics of a lookup data structure like the dictionary. Yeah, so basically what we do here, if we scroll, I'm sorry, I'm missing, we basically call contains for the list, and the search term is always the last item in the list for this benchmark, so it's the worst case. And contains key, of course, we will see how this measures, or how the performance results for this will be. I've also have some input-output benchmarks. So what did I do here? I used RavenDB in the first benchmark, and this RavenDB runs on the same computer as the benchmark process. So what we are basically measuring here is how much overhead is there for inter-process communication within or on the same machine. And the other example is here using entity framework, where we do basically the same thing. We always load a single entity, but as it is common in relational database systems, the data for a single entity might be spread across different tables. So we do a few joins here too. All right, so I hope this gave you a quick and comprehensive overview. Let's look at the results of these tests. Okay, so what do we see here? On the left hand are all these small counter increments. So we have the static method, the instance method, and you see that all these calls, even the call to a new struct, are always in the range of picoseconds. That's why it is in bright green. The first thing that comes or hits the eye is that a new class is not in the picoseconds range on my computer. And I should say that too. I tested this on Windows 10, and this is my CPU that I use. It's a 16-core 5950X. And I'm sure I will also provide you with the source code and the slides, so you can run these benchmarks on your own computer if you want to. Okay, so if we allocate, then we're suddenly not in the picoseconds range any longer. And what was interesting to me when I first heard about it is how expensive throwing and catching exceptions actually is. So maybe what I should tell you first about this chart. It's a non-linear scaling. So let me quickly change the scaling to linear so that you can see what is actually going on. I'm sorry, I have to go here. So this is a logarithmic scale, and I choose this logarithmic scale because I wanted you to see some bars. If I change to a linear scale, you can see that you will see mainly no bars, and that's because I/O is so much slower than in-memory operations, basically. So what you can only see tightly is the I/O to the same machine, but I also added another test that I didn't show you just now in the code. This is actually what's representative of real I/O. That's where I loaded an entity from a database server where I connected via VPN to my company's network. So this is actually I/O that involves hops. And this should give you a hint about that I/O is really expensive in contrast to in-memory operations. Okay, so, but when you look at the length of these bars, don't think that newing up a class and then calling a method is half as fast as, is half as slow as throwing and catching an exception. Just look at these numbers on top of here and try to divide them. And then you get an understanding how much magnitude there is in between. All right, so let's continue. What's also interesting, throwing and catching an exception is actually more expensive than running a simple operation on the thread pool. That was really interesting to me. And of course, as you might have guessed, newing up a thread is way more expensive than using an existing thread from the thread pool. So, well, yeah, maybe you had this in mind, but this is mainly the reason the thread pool exists. So we do not have to handle these really expensive thread objects ourselves. All right, let's go on to the data structures. You can also see here that I didn't even include the list of 1,000 strings because of the constraints in size on this chart. But as you can see here, it scales perfectly linear. If you look at these two results for 100 strings in a list and 1,000 strings in these lists. So we are at about 265 nanoseconds, and here we are at 2.7 microseconds. So this is what we would expect from a linear search. But in contrast to that, a dictionary has a linear lookup time, which is what the dictionary is great for, or can be used to reduce lookup times. Okay, and then at the end, you can see again that I/O on the same machine is in the high microseconds. And if you actually involve hopping to other nodes in the network, then you're already in the milliseconds. So what should you learn about what should we learn from this chart? First of all, as we saw on the left side, multi-threading has some kind of overhead, and you usually can run several thousand or at least several hundred primitive operations before parallelizing even does make sense. So I've argued with some of my colleagues that where we didn't know when should we put off some work to another thread, especially in front-end applications, in desktop applications, where we were arguing about how many load do we actually have until we freeze the UI thread. And the answer to this is always measure. And if you see something, some operations that are long-running, then is the time to load them or to let them run on a background thread instead of a thread that's the UI thread, basically. So we also saw new threads are expensive. We already talked about that. And that exceptions are extremely expensive in contrast to other control flow mechanisms like if, else, or the loops, and so on. Yeah, and I/O is way more expensive than in-memory operations. And what I want you to do, or want you to encourage, is try to measure by yourself. So these results that I've shown you are valid for my machine. I'm on a Windows machine with the CPU that I've shown you, and I ran these tests on .NET 5 on a certain version. And if you run this thing on Linux, you will probably get different results, especially if you change the CPU. But the idea is not to give you absolute values with these charts, but just hint you to what operations take how long in reference to each other, so that you have a basic understanding. Oh my God, I didn't know that exceptions are so expensive, for example. All right, so the most important thing that you should worry about is how well does my code scale? And this is basically the end of the first section. So if there aren't any more questions regarding this section, I would move on to the next, where we will talk about thread stacks and the managed heap.
No questions so far. So I posted it in the chat. So please just pose the questions if you have them, and we will answer them in the Q&A section or after each section. Yep. So Kenny, please, yeah, go ahead.
I can continue.
It's very interesting.
Right. Cool. All right. So let's continue. We will talk about thread stacks and managed heap. And I have a little example application that we will shortly run through so that you get a basic understanding about how a thread stack and the managed heap will be manipulated when we run our code. So I'll try to put this on the left-hand side. And we will have a look at this application on the right-hand side. And it's really just a simple program so that you can easily get an understanding how the, sorry, I already changed slides. Okay, so we will basically debug this application on the right and then get an understanding how the thread stack and managed heap behave over time while our code executes. All right, so let's step right into it. I hope I have, no, I didn't, of course. So let's start a new instance. All right, so the first thing, we arrived in the main method, and what's, I'm sorry, so is there a possibility? No. Sorry, I have some zooming issues. So let's zoom this way. All right, so we arrived in the main method, and this is how the corresponding thread stack looks like. So if you don't know, each thread that we have in our process is used to run certain code on it. And each thread has its own thread stack. And the thread stack is basically there to, maintain the data that is used by all the functions that are called on this thread. So the most important thing that is maintained or managed by a thread stack are variables and parameters. Okay, so let's call our first method. We call into this make good friends method, and what's happening here is you push a so-called thread stack. I'm sorry, a so-called activation frame to the thread stack. So what happens here? When you push an activation frame, the activation frame looks like the following. You first have a look at the parameters, and you see this method has no parameters, so there will be no parameters for this activation frame. Then you push the return address, and this is basically the address of the previous activation frame. So that's when the method finished executing, we can move the corresponding stack pointer to the previous activation frame. And then you have a look at all the variables of this method. And we see there is exactly one variable in this method called my friends. So this is what we push here. And this variable is of list of person. And we don't know yet what is in there because this variable is not initialized. Okay, so the activation frame basically is parameters first, then the return address, and then the variables. That's always the same thing. Sure, if you use something like stack-alloc, the activation frame will look different and can be dynamic, but in normal methods where you don't use stack-alloc, then this is how the activation frame looks like. Okay, let's start. So the first thing we're doing here is we will call the constructor of this new list element. And unfortunately, I don't have the code for the list implementation because that's part of the .NET framework. But what we can do here is we can go to reference source, microsoft.com, and we go to list of t, and we can have a look at the constructor of this class. And we are calling basically this constructor over here. So the same thing as before. Let's go back to our slides. The first thing that we do is we call new. And new is the instruction for the garbage collector to allocate a new object on the managed heap. And what does an object look like on the managed heap? Well, each object in the 64-bit mode of the .NET Runtime has an overhead of 24 bytes. This is metadata for the object, and there are different data structures referenced in there. For example, the method table. If you have overrides in your class, then this is where the actual target methods that have to be resolved when a method is called. That's a pointer to this method table is part of this metadata of an object. And the rest of the layout of the object is determined by its fields, basically, by its instance fields. So if we have a look at the instance fields of a list of t, then we can see, okay, it has a field where an array is referenced in this items property. In this items field over here. Then there is the size, which is basically the count, and a version and a sync root. So when we have a look at the object in memory, this is what the corresponding object would look like. So this blue shade on top of it is basically the metadata. It's 24 bytes in 64-bit mode. And after that, there are all the fields that I just talked to you about. All right, so then let's call into this constructor after the new operator created the new object. So a constructor is basically I'm sorry. I have some issues here. All right, so a constructor is also a method, and it's an instance method. So when you push the activation frame of an instance method, the first parameter that goes on the activation frame is always this reference. So if you remember to assign these fields, it's not explicitly written here, but in front of this is actually this reference that references the items field over here, for example. And of course, we have the capacity parameter. So this is the second parameter on this activation frame is the capacity. We do not have any variables here, but of course, we push the return address to this activation frame. So, and this is basically how we run this code. So if we would execute this constructor right now, then we would see, we didn't pass in a capacity of 0. So what would actually be executed is that a new array with the given capacity would be allocated. And this is, of course, a new object in the managed heap. And once this statement has executed, we basically have a new array over here with 2 slots. And the items field of this object would reference it. That's what I use these blue arrows here for these references, but basically it's a memory address which is saved in this field of this object. Okay, so then the constructor is done. So we can return to our statement. And this is when the constructor is returns to the caller. So in our case, we will actually pop the corresponding activation frame. And the active method is, again, our make good friends method. All right, so let's quickly continue with creating a new person. We will jump into this create and add person method. So what we do here is always the same thing. We look at the parameters of this method, which are 3, the list, the name, and the age. We then push the return address, and finally the single variable in this method, which is new person. And let me go through here a little bit more quickly, because I think you got the gist of it. When we call this constructor of this person class, it's always the same thing. We push this reference because it's an instance method. We allocated a new person object, and we have the name and age, and then assign them to, I'm sorry. Okay, interesting. I think I started, no, I'm sorry. I hope I can continue debugging. No, I can't. I'm sorry, I accidentally started another application. Okay. I have some debugging issues, which are not great. So let's make it the startup project. Okay, so, all right. So after we created this person object, then we can assign, and we assign the corresponding variables to the field. Then we can go back to our caller and then finally add the corresponding person object to the list, which in turn is just a add to the corresponding array. So the first slot of this array now references the newly created person object. All right, so, and I'm sure you got the gist of it. So if we now call this method again and go back here, then you can surely imagine how this thread stack and managed heap behaves over time. And so we will have another object over here where we created a person called Jesse and added it to the list. And this is basically how the corresponding thread stack looks like when we are done with this method. All right. Okay, so why did I show you that? Because for a long time, I didn't realize how this actually works internally. And I didn't have or I made up some primitive understanding because of how C# is structured. So maybe a thing that I thought about was valid is that a variable that is within a for each loop will be several times present on the thread stack, but that isn't true at all. So it doesn't matter how many blocks you have within your method scope. It's always so that all variables are just pushed before the beginning of the method execution. So it doesn't matter if you have variables in for loop blocks or any other sub-blocks in your method. It doesn't matter. They are basically hoisted. So if you ever programmed in C, then you can maybe remember that you always had to declare the variables at the beginning of your method. And that's basically what the C# compiler or other compilers do for you in this regard. So the idea is that you have something to argue about how your code will manipulate memory. And this is, for example, for me also extremely important when I learn new languages, because a thread stack and the heap do behave quite similar in different languages too. So if you're starting maybe to learn C++, then you can suddenly argue, okay, I have a thread stack here, and in C# there was no possibility to allocate a reference type on the thread stack, but with C++, I now have suddenly the option to allocate a class on the thread stack too. And I think talking about thread stacks and the managed heap and have a good visualization of it is a great way to learn new languages and argue about your code and how it will behave when it is executed. Also to find maybe something like memory leaks or anything else in this regard. All right. So I don't know what went wrong here, but let's go back to the slides. So I also summarized everything here that we just talked about in this on this slide. I think I have an issue with my keyboard. Okay, I don't know why. Okay. So all that I've talked about here is basically how you should, how you should imagine how memory looks like when you execute your code in the .NET runtime. And as I said before, I think this is a great tool for us to have a visualization of how our code executes and what is involved, especially when there are many object allocations involved and so on. All right, the next topic, garbage collector runs. So if there aren't any questions, Igor, how does it look like?
Yep, so far, you're free to go.
All right, cool. Then let's continue. Okay. So, Konrad Kokosa actually posted a great general overview of how the garbage collector operates when it executes a run. So this was great, a great introduction to me to before doing something similar that might be not as sophisticated as his picture. So what does the garbage collector actually do when it runs or it wants to deallocate memory? So I'm sure you heard about the generations in the small object heap. And the first thing that the garbage collector does is deciding which generation in the small object heap actually should be collected. And once this is done, there are basically two modes that the garbage collector can run in. And one of them is the so-called background GC, which means that the garbage collector is able to run while our main threads execute our own code. So before I had the understanding that when a garbage collector run is performed, then actually all threads stop working while the garbage collector performs its run. And this is not true. There is a mode where the garbage collector can perform a concurrent mark and concurrent sweep phase while our other threads are running most of the time. So there's a small preparation phase in the beginning and a small phase at the end before the sweep begins. But basically, there is a mode to run while our own code is still executing. What's not possible in this mode is that the corresponding memory cannot be compacted. So For this, there is the foreground GC mode. And the most important thing about the foreground GC mode, which you can see here on the right side, the left one is the concurrent background mode, is that there is actually a plan phase. So when I started learning about the garbage collector, I was under the impression that the garbage collector actually has 3 phases. So the first one is the mark phase, where it traverses all the things on the managed heap, all the objects there, and every object that he visited is marked. And objects that are not marked can be later deallocated in the sweep phase, which I thought was the second phase of the garbage collector. And afterwards, there is a compact phase where the resulting holes in memory are actually defragmented. So other objects are moved so that the memory is most compact, and the next new free position in memory is at the end of this whole memory block. But if you've read Konrad Kokosa's great book, you actually know that this is not necessarily the case, because in the second phase of the garbage collector run is actually a plan phase, where the garbage collector tries to perform a virtual memory compaction. So it tries to utilize the memory that is actually deallocated. So the garbage collector team talks about so-called gaps and plugs. And gaps are locations in memory that will be deallocated. And these gaps are used to perform a virtual compaction and then decide, based on the resulting statistical data, if an actual compaction makes sense or not. And this is what you can see here on this decide on compacting step. And based on the result of that is either the relocation phase and compact phase, or just the idea that, or just the operation that the corresponding memory is freed, and a so-called freed list is upgraded so that the garbage collector knows internally where free regions in memory actually are located. Okay, so we already talked about most of this. The most important thing is maybe to know that there is a concurrent background mode. There's also a different mode between workstation mode and server mode. And the basic thing to know about workstation versus server mode is that there is basically a managed heap per thread for the server mode. And this allows deallocating or performing garbage collector runs with less thread synchronization. But in turn, you will consume way more resources. So my basic recommendation is, if you have several apps that run concurrently, or for especially service apps, if you have several service apps that run concurrently on the same server, on the same VM, then you will probably should favor workstation mode. Because if you run in server mode, you will have great overhead per process, and you really have to measure if that's the thing that you're going for. But it might reduce the latency on your services. But generally, I would recommend server mode if you have a lot of resources on your VM, which might not be the case, or if you only have a single app running on that server, because it's that much requests that you have to handle. All right, we also talked about the 4 phases, the mark, plan, sweep, and compact phase. And as I've said, depending on concurrent background versus foreground modes, only 2 of them might be actually executed. And we also talked about the small object heap and the large object heap, which was actually extended in .NET 5 to the user old heap. In .NET 5, the garbage collector got extended. You now have the possibility to have pinned objects in their own heap. And this is called the pinned object heap, so POH. And as the pinned object heap is somewhat of an extension to the large object heap, both of them are combined under the term user alt heap right now. But this is only valid, as far as I know, for .NET 5 and later. Okay, so you probably also know that the small object heap has a hard size of 85,000 bytes. I'm sorry, that wasn't well formulated. So if an object is less than 85,000 bytes, then it's placed in the small object heap. And this is usually where our objects are allocated, but there's also a large object heap, but most of the objects that we allocate there are simply large arrays. So usually byte arrays where if we load a really large file into memory, that's usually where these large arrays are placed. And I would recommend, if you can, avoid the large object heap. Many of the optimizations that were done within .NET Framework resolve around having buffer sizes around 30,000 bytes. If you look at the string builder, for example, or if you look at the segments feature of the pipes, then these buffer sizes of around 30,000 bytes are usually used. And if you require more space, then several different buffers are just appended to each other. Okay, what we didn't talk about so far is how does the garbage collector actually start when it's performing its mark phase. And this is done through so-called GC roots. And of course, we have to know what GC roots are. And these are all variables and parameters on all thread stacks. So these are the entry points for traversing the managed heap. Static fields, of course, too, objects with finalizers and destructors, and pinned objects. These are the GC roots where the garbage collector can start its runs in the mark phase, or its traversation of the managed object heap. And why is this important? If we think about how do we program with and not against the garbage collector. So the simplest rule is basically, if you don't allocate, the garbage collector won't run. So I wasn't sure, because when I learned C#, there wasn't there wasn't any lesson about when does the garbage collector actually start running. The message always was, well, it runs at points in time that you cannot determine beforehand. While this is somewhat right, the answer is pretty simple. If you don't allocate, the garbage collector won't run, probably. There is a small exception to this rule. It's when a thread gets deallocated, this might actually lead to a garbage collector run, but it's very, very seldom that this is the case. The other point simply is the garbage collector will perform its run when the corresponding allocation contexts are well out of memory, so to speak. So if there isn't enough space for allocating the next objects, this is when the garbage collector will perform its runs to free up more memory, to relocate the allocation contexts so that there is memory to allocate to. So if we want to write high performance code, and we should perform the most important calculations in such a way that we don't allocate. All right. And yeah, the idea is, if you still want encapsulation in these circumstances where you do heavy calculations, then you could use structs instead of classes, because as we've seen in the performance slide before, using structs is something that usually is the garbage collector usually doesn't care about structs that you allocate, because structs by default are either part of other objects or are part or directly placed in variables / parameters on the thread stack. And the basic way of thinking is reducing the amount of stuff that we do on the managed heap and instead shifting all these calculations to the corresponding thread stacks where we execute our calculation. Of course, as we've seen before, we should reduce the number of threads per process that we allocate. So we will talk about this later, but I can foreshadow something. The idea is if you run on a CPU with 4 cores and hyperthreading or simultaneous multi-threading, so this around 8 cores in this case, around 8 threads would be an ideal number, because threads in itself are quite expensive objects, and the more threads you have, the more overhead you have. And you should place the optimal amount of threads around the number of CPU cores plus maybe the option to have simultaneous multi-threading, so that you can usually execute 2 threads per core. Also about these allocations on the managed heap. We saw the new keyword in our small example, but there are also always a number of hidden allocations. So if you're using lambdas and you use closure or lexicoscoping, this usually allocates. It depends on the case. It could be an allocation per call. It could be an allocation per method, but where the call is actually performed. But if you want to avoid these, then don't use closure or lexicoscoping. Also very important, do not block threads on the thread pool. We will come to that in the next section. String concatenations is also clear. Strings are immutable. And if you concatenate a lot of strings together, then each concatenation results in a new string. So a string builder or interpolated strings might be more useful in this case. And there are also a lot of frameworks, a lot of algorithms that perform reflection on each calculation. So examples for these are, for example, data binding in WPF, or if you have ever used it, the Unicontain less than version 5, or serialization frameworks, for example, JSON.NET, or some object relational mappers. Once you perform the main calculations that you do with these things, so pushing data from a control to a view model or resolving an object graph, if each of these calculations or operations result in a reflection-based algorithm, then this usually allocates per call, and this is bad. So what happened in the last years is that a lot of these frameworks / libraries went over to code generation. So on the first call, maybe, for example, on light inject, which is a DI container, light inject will create or generate code and compile it dynamically during runtime, where you generate an optimized version for resolving the corresponding object graph. And once this optimized code is generated, it will be called on every succinct call to ref. And this is usually way better if you perform a calculation many times over, like, for example, also deserializing the same JSON documents only with different values over time in a web service. This is usually way better than to run reflection on every calculation. All right, if you want to learn more about it, Igor already said it in the intro, please read this book, Pro.NET Memory Management. It's one of the most important books, I think, that has been published in the last years, because it gives you really, really great insights in how the garbage collector works internally. And, well, basically, all my knowledge that I have is based on this book. And it's really great. I simply can't tell you the amount of work that went into it. I think Konrad Kokosa took about 3 years to write this book, which is 1,200 pages, around that. And it's really worth every penny.
You shouldn't scare people with the number of pages, but there is a lot of also very, very actionable advices in the book, and so not only in-depth theory, I have to say. So it's really, really good. Okay, not from my side. Kenny, just to remind you, so it's 7 p.m. now, so that you have also an idea about the time.
All right, this is actually the end of the garbage collector section. So let's move right on to asynchronous programming. And just let me quickly reiterate what asynchronous programming means. It means that we start a call, and this call returns to us while the corresponding side effect or return value isn't calculated yet. And usually we can do something else while we wait for the results to actually be delivered to us. And this is usually done via an event-like mechanism. And why do we want to do asynchronous programming? Usually because it's either CPU bound or IO bound. And I would even argue IO bound is the more important scenario. And why this is the case, I will try to show you this in another example. So let's stop debugging here. And let's go to this example here. All right. So let's go into release mode. And I've started this ASP.NET Core service over here. And it's a regular ASP.NET Core 5 MVC application. And it basically has a single controller with 2 actions on it. And what we can see here is that we have a synchronous version of this action and an asynchronous one. And what I do here is I either call thread point sleep or a task delay in the other case. And after I've done this, I simply call update used threads. And in this thread pool watcher class, what I basically do is at the end of each action that is invoked, I'll use simple or very inexpensive thread synchronization methods to check how many threads were active at the same time. So basically, at the end of each of these actions, I'll just check, okay, how many threads are currently active on the thread pool, and the maximum is stored. This is what these controllers actually do. All right, and I wrote a WPF client. Well, let's start this too. Okay, and I also disabled logging, so don't be suspicious when you don't see any logging statements over here. This WPF client will now perform 1,000 HTTP requests against the service, and the wait interval for the thread.sleep or the task delay is 1 second in this case. So let's start this call. And we see that the call actually finished pretty fast. So it was 1.25 seconds, and 33 threads were used concurrently at the maximum. So this is a great deal for me because my computer is a 16-core CPU with simultaneous multi-threading, so I can handle 32 tasks at the same time, or threads at the same time. So this is great. So, and now let's switch to the sync API. And you can see already that it will take a little more time to finish. A little more than I expected, actually. All right. Okay, so this took about 23 seconds. And we actually now have way more threads than we actually would need. So we have now 55 threads active. And why is this? The important thing that you have to realize is that when you block thread pool threads, then you will basically instruct the thread pool to create new threads. So the basic algorithm is when you put work against the thread pool, and the thread pool sees, oh, one or several of my threads are actually blocking, and I don't know when they will be available yet, so I will create new ones. So the basic understanding about async programming that you should have is that the thread pool will create new threads when it sees that its threads are currently in a blocked state or sleeping state. And as we've seen before, threads are pretty expensive objects. Let's quickly talk about how expensive they actually are. So a thread stack, as we've seen before, for a thread is 1 megabyte in 32-bit mode and 4 megabyte in 64-bit mode. Well, not all of this is actually allocated, but all of this is reserved, and it might be allocated later. Then there's also a kernel mode object, which is 14 kilobyte in 64-bit mode and 12 kilobyte in 32-bit mode. And this kernel object is basically used to preserve the state of the registers when a context switch is happening. And context switching basically means that the operating system stopped a thread from executing and decided that another thread is now able to run on the corresponding CPU core. And context switching, of course, has some overhead too, because if a new thread starts operating, the amount of cache misses will be pretty high when it starts to run, because these the data that the previous thread used is probably not the same data that the new thread will use when it starts executing. So, well, why is this async I/O important? Basically, the async I/O to other third-party systems like databases, web service, and so on. When we do this synchronously, as I've said before, the thread pool will create new threads. And I also want to mention that some packages or some data access libraries, for example, the one of Oracle, if you want to connect to Oracle via their official managed drivers, the unfortunate thing is while there are async APIs that you might see, the corresponding driver is not implemented in an async way. So although you think you might actually perform async calls against an Oracle database, they are actually synchronous under the covers. And so I would recommend that if you want to write a high scaling web service, you should also check the data access layer, the corresponding NuGet packages that you use, if the corresponding drivers are actually provided in an async fashion too. Okay, so if we take another look, how could this look like if we actually do async operations or async access to third-party systems? What happens is when a async request comes in as maybe an HTTP request for a service, then one thread of the thread pool can start handling this request. And when this thread then starts async IO, this operation, well, basically then returns the thread pool to the ASP.NET Core application pool so that the corresponding thread could handle another request. And that's why the first call to this asynchronous method was actually that fast. And what probably happens is when your async IO request returns, then it could be, or it's pretty likely that another thread in the thread pool actually handles the rest of the request and writing the response. So if you write asynchronous code, you should keep in mind that during a request, you might change the thread you're executing on. So thread static isn't maybe the greatest idea in this case if you have any functionality that depends on that. All right, what's the overhead of async methods? That's actually quite hard to reason about because it's pretty hard to measure. Because when you try to invoke an async method, there's a lot of things in place that, or a lot of stuff executing in the background too, and you will also measure this too. But I would say, or I would argue that you're at least in the microseconds when you execute an async method. So the idea that, how should I put it? Just make every async or every method async isn't a great idea in my perspective. So you should make a clear distinction what is an async method. So basically what is IO and what is not IO. And I would argue to not make every method async. All right. Okay. What is going on under the hood? The compiler actually transforms any async method into a state machine. And if you want to, we can have a look at it after the talk in the questions section. I also have an example where we take a look on memory maps, how the state machine is actually transformed and then executed. All right, and yeah, the maybe interesting thing is that if you have a synchronization context, then the corresponding continuation will always be executed on the thread that belongs to the synchronization context. If not, then the corresponding state machine will queue the continuation on the thread pool. Okay, but yeah, async IO is especially important if you want to scale out with a single service, because if you don't follow that, you will create many more threads in the thread pool than you'd actually like. Okay, I have another example of how a async method, or what an async method, in this case, writing a byte stream to a file, actually works internally, but I will skip that for now. If you want to, we can talk about it in the question section. All right, so let's go to the final section. I'm warning you, these are highly subjective matters, and they are maybe not that well formulated, but I think it might be the foundation for a discussion afterwards about how we structure our code. And well, let's just simply start. let's talk about the solid principles first, because it was maybe the one principle that I got completely wrong when I was a junior developer. And the single responsibility, I'm sorry, my keyboard is not doing what I wanted. I'm sorry. So the single responsibility principle basically says a class should have one reason to change. And what I misunderstood back then was the term responsibility. I thought it was a single functionality, and that's mainly the reason why I created so many small classes, as I said in the beginning. But this isn't actually the case. If you have a look at the slides later, I will give you the link to the GitHub repo. In this video, Uncle Bob Martin actually explains that it's basically designed around people. So which people have which responsibility, and you shouldn't mix up several different problem areas within the same principle. And well, that would be an appropriate description, but why not name this principle single problem area principle in this case? I think it's more intuitive this way to indicate that it's not about a single functionality. All right, let's talk about the dependency inversion principle and the OCP. So dependency inversion principle basically states program against abstractions, and these abstractions should be modeled in their own level. There shouldn't be any details of any abstractions found in the abstractions layer. I'm sorry, any details of any implementation found in the abstraction. And if I look at the OCP later, if I can, now it's working. So the open-close principle basically says that software entities should be open for extension, but closed for modification. And I would argue, while they may be conceptually on a different level, they basically say the same. Namely, use abstractions or indirection loose coupling when you call from one element or from a caller to another piece of functionality that you want to reuse. And I think, for one, we could combine them because they're pointing basically at the same target. And secondly, I would also argue this isn't always necessary, because what you end up with is a lot of indirection. And a lot of indirection with maybe together the misunderstanding of the SRP that you have many small classes might also lead to some kind of spaghetti code. Yeah, it's loosely spaghetti code or loosely coupled spaghetti code, but it's still not that easy to read if you have many small classes and all these abstractions in between. So I would argue, why shouldn't we combine them and make them realize indirection is great, but maybe not in all circumstances? I would also argue that we should, especially for new programmers, we should also give them a principle called learn the internals. And this principle basically says you will not reinvent the wheel. You will run on existing runtimes, on existing frameworks, on existing libraries. And as a developer, you should have a basic understanding, at least at the top level, how these things work internally. And especially, you should be worried about code that might hurt these libraries or runtimes. And if you know about this, then you can try to avoid this in your code base and try to achieve a state of, when you write new code, it will probably be good because it respects the internals of the corresponding frameworks and runtimes you're running on. I know this is something that goes a little bit against encapsulation, But I still think it's a great idea to learn the internals, because you will suddenly structure your code differently to get more optimal, to get more performant results. I would also introduce a new principle that's called respect the process boundary. And what this actually does is telling programmers that they should make a clear distinctions between operations that are performed in memory and that are I/O operations, where the state of a third-party system is involved. Mainly because, as we've seen before, async I/O matters if you want to scale out. And it's also way easier to test operations that only act in memory instead of operations that also involve a third-party system like a database or another web service or the file system, where the file system obviously is the easiest one to set up a mock for, or even include it. But I think you get my point. So we also have a principle that I somewhat want to capture and that I've actually forgot about for a long time. But I want to somehow reinvigorate the IPO principle. The IPO principle basically says, or it was basically used in system engineering in the early days of programming, where you have a dedicated input or a schema for input, and then the whole processing stuff and the corresponding output. So this was also mainly used in designing operating systems or, for example, all the commands that you can call on a shell. But if we somewhat capture the essence of this IPO principle, we could well translate it to the apps that we are writing today. Like we have a certain amount of input that's maybe coming in from an HTTP request. Then we validate it. Then we maybe load some more data from our internal third-party systems. And then we perform some process, which is basically in-memory operations. And then we create side effects or write a HTTP response, and this is the output. So if we think about this thing, we could say, okay, the input and output can always be async, and it should be loosely coupled. But the processing part in between, well, these are always in-memory operations. And if I want to, and maybe even if to reduce the complexity of my code, I could argue to make a tightly coupled version there, because it will be still easy to test, because these are just in-memory operations. You will probably test a little bit more than a single class or a single function, but these tests will run fast because they are in-memory operations. And the more you test in one unit, I think that's maybe something to achieve, because you will write less tests and maybe test the same functionality overall. Okay, so I will also want to make a point about imperative code and static methods, especially if you write orchestration code. We had a tendency to have very, very abstract components sometimes. Maybe they are even described in YAML or some other exotic languages. But what I found interesting about this development in the last years is that this declarative way of programming might not be the best thing if I want to see what some orchestration code actually does under the covers. And I think, or my favorite for orchestration code right now are actually async static methods that I can use where I have all the statements one after the other. I can clearly see which calls perform an async I/O operation. I can clearly see what is performed afterwards, and I can clearly see how the result is assembled, or how the side effects are saved, or something like that. So I want to incentivize you that imperative code in this case is a great way to structure orchestration code. And in simple circumstances, it might be even enough. So you don't have to introduce other objects that make your dependency graph more complex. And static methods, as we've seen in our overview, are also pretty fast. So you will have less objects in memory. You will have fast calls to the corresponding methods. And as long as you abstract away I/O, you will still have great possibilities to test this code. Okay. What I developed at our work, the main reason why I developed this is to give a really simple model how to structure processes in our application code. So what you see here is basically all that I talked about beforehand in one picture. We have the core, which is basically the processing part of the IPO principle. And the important thing about this core is that it's completely isolated from any I/O. So if core functionality wants to perform a database call and so on, then this has to be done via this abstraction over here. So you have to have an interface, an abstract base class, a delegate, whatever, some kind of indirection in place when you want to call or make I/O calls. So, and humble objects here are actually there to perform these calls in production environments. But as the name says, humble objects are really, really simple objects that manipulate a entity framework database context, for example. So that the corresponding data is loaded or updated and then saved. And these humble objects are so easy that I usually do not need to test them because they're easily written and they can be checked easily in a code review. What I can test or where I would write automated tests, let's put it that way, is about the core. But as the core is completely isolated from any calls that cross the process boundary, I can easily test them and I can run lots and lots and lots of them in my unit tests. And as long as I don't perform I/O, these tests are fast. And I don't even need loose coupling in the core if I don't need it. So again, I would like to stress, you can run many tests and even with code that is tightly coupled. Yeah, and the last thing within a process, in my opinion, is the so-called composition root. This is where you assemble all the different pieces in your app. This is where you set up your DI container if you want to use one. And an important part of the composition root is also the resolve phase. So all stuff that sets up operations is also part of the composition root. And this is the culmination of all these design principles and stuff that I talked about earlier and simplified in this single piece or in this picture. All right, and last slide. I want to end with the resist the hype principle. What I also had always in my career is certain time periods where I always wanted to use something new. Like maybe what? So I can remember times where I learned about the chain of responsibility principle. And I just implemented it in one of my tickets that or one of my tasks that I had at work, just because I could do it or I wanted to try it. And I would also say we need a principle where we slow down developers, especially young and hungry and new developers, where we tell them that they should first take a real close look at the tools, at the frameworks, at the patterns or whatever that they're trying to introduce so that the hype that comes with a new technology, the hype that comes with a new framework, and so on, is somewhat alleviated with or grounded against the prospects of reality. So maybe this is the last thing that I want to give you today, because that's the end of my talk. Thank you very much. There are several, sorry, my keyboard is still messing up. So there are several, no, my keyboard doesn't like it. I'm sorry. Okay, there are several sources that I want to give you. I will also translate this. This is still in German. I'm very sorry. But as I said, Pro.NET memory management, it's really great. Advanced threading in .NET, that's basically my introduction to how does the thread pool and threads work, how do you deal with asynchronous programming. These were basically my main sources, and I also recommend the other stuff. And that's when I say thank you for your attention. If you have any questions, please feel free to ask them.
So thank you also, Kenny. So far, there were no questions, actually, at least not direct in the chat. I would invite everyone if you still have some. So there are plenty of people still here. So if you have something you would like to ask, and it's short enough to be typed in quickly, please still have some chance. So Kenny's here. If you have any questions, feel free to ask. Mm-hmm. We'll wait a bit. There is a nice one. Thank you for the presentation. Yeah, definitely. Kenny, thank you for the presentation.
Yeah, what we could do while some people are think about their questions is I can give you the link to the repository.
Yeah, basically, so all the links which we shown will be in the Meetup.
Yep.
Anyhow, but yeah, basically said. Conrad is saying thanks for the mentions, so that deserve definitely.
Thank you for your book.
Yeah. Okay, so I would say if there are no other questions, thanks to everyone for staying this late. This was our first streaming this year, so we're going to continue most likely in a monthly pace, and somewhere nearby future we will also have another one in the Hyperf series, as I said. Maybe you can, Kenneth. So just to answer it, there is a question for the link. We will paste the link. Will be on Meetup, so just take a look here, or we can also paste it. Ken, if you have it, let me just. I will paste it here also in the chat. I think it's gonna be.
Yeah, I pasted it in the private chat.
Yeah, I'll paste it immediately so that you have it here. So the examples are there. Okay. Thanks, Kenny, for sharing your knowledge and experience, and thanks everyone for staying with that. Oh no, there is a question. This was the last moment one.
Okay.
This is an interesting one, so let's have it from Christian. Thanks for asking, Christian.
Yep.
Tom, Kenny, you can address it.
Yep. Okay, so the question is going from sync to async implementations. This will change the signature or the return values of your methods, basically. And that's correct. This is actually quite a lot of work if you have to go the hard way and change everything up the call stack. if you use something like ASP.NET Core MVC, then you have the option to do that without that much changes, because you can migrate any controller on its own, because ASP.NET Core MVC understands if the action is asynchronous and thus calls it differently than a synchronous one. But if you have it in any other kind of application, I think especially front end, then you will have to adjust every method signature. And this can be quite a lot. So unfortunately, I don't have any proposition on how to do this more quickly. So I would just recommend doing it step by step.
Maybe to that question, I could also show something. Let me just say to that question. Okay, I think I can share my screen. It's a good practical question. So we had this, just a second to see if it's working. So I'm revising a bit right now. So that's a C#5. Yes, so this is exactly this one. So let me just share my screen. Pop. I find it important. In practice, if you all think about that example, which was, by the way, Kenny, excellent example with the WPF application attacking the server with those 1,000 concurrent calls and so on, where actually we saw what does it mean to have an async background or not to have an async background. In practice, like, it definitely makes a difference. And so here, for example, in this, you can see it in this tool called Sharpen. What it does, it analyzes actually your code and suggests you to use, let's say, new C# features or certain C# features. And in this, I have some dummy solution here. So it will suggest you for C#5 some async and await things. And sometimes it tells you really like await equivalent asynchronous method. This usually means that somewhere in your code, for example, these are the dummy examples. I didn't open now a real life application. But for example, it will tell you, oh, you have already an async method and you are calling a blocking method, which is actually, I would say, a bug. But the interesting thing is this, what Christian is asking is this one. And the phrasing for me interesting, it's consider awaiting equivalent asynchronous method and making the caller asynchronous. So what it does is the following. It will, for example, recognize that this what you have here is blocking, but there is an async method, okay? And it is suggesting you exactly this what Christian is saying, okay, I could have a better performance here and so on. But what I'm trying to say, this part, the considering, so I plan to add explanations for it and so on, means you have to think of the things which Kenny was mentioning, and also think of, okay, do I really want to do it? What does it mean? In practice, it definitely means going like bottom up or however, and changing the whole colors, and often it means changing the architecture, like in general. We did this exercise in a workshop we have on, it's called High Performance ASP.NET, where we're explaining the thing which Kenny was showing, and then really doing this exercise. Okay, what does it mean? Assuming that we have a code which is synchronous, we see issues with it and so on. So how to make it asynchronous? The tool was giving us suggestions where we have possibilities to improve, because actually it finds the places where you can have an async equivalent. But the work is, let's finally, like, you have to pull. Yeah.
You have to type yourself.
Exactly, and do the work manually. Yeah. So that would be, let's say, the short answer.
But this might be an idea for a Roslyn analyzer and code fix. Might be.
Because I was thinking
of. Yeah.
I'm sorry. Yeah, please, can you? Yeah. What is it like for these which are clear, like await equivalent synchronous method? It's a clear statement. Do it, and then the fix is there, because the fix is deterministic also. But for this, what Christian is asking, like with the considering stuff, It really depends about a lot of things, who is using your libraries and. So it's actually re-architecturing on a larger scale. And I expect the human brain to be involved in that, to really take a look and say, okay, first of all, do we want to do it? Yeah. Will it bring us something and so on? If you have a backend that serves 10 users, it will not pay off.
Worth the hassle.
It's not. Yeah, definitely not worth it. But for example, after one of these workshops, there was a feedback I got afterwards in an email, and I really like it. The person was saying that they actually did it. They had instabilities. We were discussing it also in the workshop. Why? Because it happened simply. They were actually mixing. They would have an async method which had the blocking codes and blocking calls and so on. And after the manual cleanup of the things, I got a feedback that actually the backend got more stable. But the message here, Christian, is yes, it's hard. You have to judge, consider. Judge it if it's worth it, and then it's a manual way all the way up, a manual work all the way up. Yeah. Good. Couple of other thank yous. We have another one question which is also related to async await. Maybe Kenny, you can address that one as well.
Yeah. The question is, does async method that doesn't execute asynchronously, e.g. await part not called, incur some performance hit in comparison to non-async method? So because every async method is actually transformed into a state machine, there is always overhead. An async method will, there are also memory fences in place for CPU core synchronization. And there is always an overhead if you call an async method. And if you don't await it, this simply means that your calling method will continue executing after you started the asynchronous operation. If you await it, then you will be signaled, and the corresponding state machine will jump to the correct position to resume the continuation afterwards. So not awaiting per se is not a performance overhead, but making a method async, this will result in the C# compiler transforming it to a state machine. And calling this method in the first place is the overhead that is incurred here. So if you call that method that is async, it's always a little bit of overhead. And using the await operator means that you also have the memory fences in place that I just talked about.
Good, thanks, Kenny. Christian is saying that he's working on exactly such a project. So moving. So Christian, what to say? I hope it will pay off, that you consider it wisely. Good. So thank you. So thank to everyone saying thank you. And if there are any other questions in the last moment, then I will also say thank you, Kenny, for joining us. And
thank you for having me.
Great for having you always. And bye, everyone. Have a nice evening, and see you in a month, roughly. Yeah.
Bye-bye.
Thank you.
Enjoy the evening.